Hello, I am Geoff Kimm and am also presenting on behalf of my co-author Mark Burry. Our paper proposes a novel contribution of community participation through reactive scripting for design in decisions that have major long-term implications. The research is based in a context of smart villages and rural development. The computational framework we propose addresses the use of digital built environment simulation with embodied responsive expertise modelling to facilitate participatory processes in situations in which guiding expertise is of limited availability. The villagers involved can be considerably more enfranchised in processes typically done for them by invisible others or not done at all. This presentation is organised into three key parts: the research context, the reactive scripting framework, and a prototype app and outcomes. The research is grounded in part in our association with the Smart Villages Lab, University of Melbourne. The lab focuses on rural development in the state of Assam, northeast India, and in particular the island of Majuli, pictured here, on the massive Brahmaputra River. Majuli well illustrates our rural context. It is an area of relative poverty, low development, and remote from centralised government. There is a growing focus on smart city solutions to some of the problems caused in developing Asian cities by rural flight to those cities, including the use of collaborative and collective design and governance techniques. There is no commensurate technology-enabled focus, however, on the issues within rural communities. This imbalance risks a self-reinforcing negative rural outcome. Solving the problems of the cities, while necessary and worthy, increases the pull factor, and the abandonment of the rural only encourages the push factor to worsen. Deloy et al. Identify a central challenge in the nature of top-down governance, and I quote from the reference: "Every rural community is different, and it will take unique insider knowledge of the region's assets and customs to determine the most effective combination of policies, and central government generally devises a single policy for all rural communities under their jurisdiction, which can be hundreds or even thousands of villages with differing cultural traditions, religious beliefs, employment opportunities, and standards of living." Communication can be better by reducing what is an expertise gap in governmental decision-making. At the top, centralised experts spending a society's resources benefit from the guidance of community participation, yet the most effective participation by individuals at the bottom often relies on expert guidance. In many remote and developing rural contexts, that in-field expert guidance can be scarce. This expertise gap is addressed in reactive scripting for design that brings the non-expert stakeholder more actively into the design loop as a bottom-up participant. Reactive scripting, which originates from the computer science reactive programming paradigm, propagates information within a program state through relationships linking reactions to events. Hence, iterative modelling and decision-making that focuses more on behaviour than on data is prioritised. The application to built environments was tested at a structured Galapagos Islands workshop in which multidisciplinary participants were guided by expert discussion to find mutual understanding of relationships and trade-offs between rivalrous economic, ecological, and experiential issues. However, reactive scripting for design, as tested in the Galapagos Islands workshop, is not sufficient in itself for community engagement without direct expert guidance. In response, we extend that work to introduce a reactive scripting computational framework of three integrated parts. Reactive scripting modelling of relationships that prompt users at vital decision points. Encapsulation of abstracted expert knowledge as the core driver. And visualization, interaction, and engagement techniques arising from gamification to emphasize vital relationships and provide feedback, including decision prompts. These key elements of the framework are illustrated in an early proof of concept that allows a user to explore and understand issues of urban densification. In that app, users can undertake guided participatory design of foreshore revegetation, as well as principles for building envelopes of new developments, and also see the future ramifications of decisions on mixed-mode transport. Seen here in the foreshore revegetation scenario, reactive scripting and encapsulated expert knowledge prompt the user to make decisions on rivalrous factors such as sufficient vegetation cover, safety and passive surveillance, and budget allocation. The reactive scripting framework does not use typical ludic gamification that is characterized by imposed rule-based activity and competitive goals. Instead, the alternative PIDA is used, which is the expressive improvisational fusion of meaning and behaviour, as it is best suited to capture subtleties of community preferences as well as latently held attitudes and desires. Reactive scripting was also tested in work on an algorithm that efficiently calculates shadow origins in built environments. In the demonstrator shown, users in response to their interactions are prompted with the actual and apparent causes of shadowing left and the unique shadowing contributions of buildings right. To verify implementation of the three-part reactive scripting framework, a prototype app was developed that examines introduction of community internet access and accessibility of new infrastructure in a village on the island of Majuli. The community engagement in that app was founded in a series of research projects focusing on rural development and participation at different scales. At the house scale, software was created and tested to allow householders to reconfigure a replacement home built of safer and more advanced materials, with designs that conform to an identified set of culturally loaded conditions and expectations. Similarly, a prototype digital workbench was developed at village scale. The concept helps villagers explore for themselves viable social and geospatial organisation for new settlements, as well as the modification and densification of existing villages. The framework takes into account a broad set of competing parameters that require significant trade-offs against each other, including local economic metrics, environmental impact, resource availability, and cultural drivers. It offers villagers the opportunity to test what-if scenarios of their own devising, through which solutions informed by local data would be suggested and tested for appropriateness and fit. At the district level, a survey of households in selected villages was undertaken using a smartphone app, and a data visualization framework was developed with extensions for direct community reporting of local issues. At state level, a gamified approach was tested for illustrative modelling for community awareness. In it, the road network for Assam is interactive, and users may select and configure road elements and cities to better understand road network accessibility and the benefits of potential infrastructure projects. The first mode of the reactive scripting prototype app allows users to participate in selecting the placement of Wi-Fi mesh nodes in their village to capture local knowledge of conditions and preferences that are not easily included in typical top-down planning. On opening the mode of mesh Wi-Fi node placement, a user sees a single initial network node placed at a village house. The expert knowledge kernel undertakes complex modelling of mesh network signal strengths for current node placements. All houses are correspondingly coloured, and signal strength and the total node count and limit are displayed in a UI overlay. An implicit reactive scripting prompt is given to suggest alternative Wi-Fi node placements. On selection of node number and placement by the user, a genetic algorithm within the expert knowledge kernel responds immediately to reconfigure placement of all non-fixed nodes. Its exploration of the solution space, which otherwise would be near instant, is slowed to human perceptual scale and concurrently displayed, along with a prominent thinking brain icon in the UI overlay, so to suggest alternatives as it converges on an outcome. Here, a user has added a Wi-Fi node to an important house and fixed it in place. In accordance with paid gamification, there is no prescriptive goal in the prototype. Instead, users may, when asked to select the number and preferred location of mesh network nodes, bring to the simulation those considerations not directly embodied within it. Users have unique local knowledge of special considerations allowed for in the model, including where and who is important in the village, budget and project prioritization, and number and placement of nodes. An explicit reactive scripting prompt is given when the genetic algorithm cannot dynamically update the simulation with a node configuration that gives a preferred level of signal coverage. In such a case, an interactive traditional Galab Jaman suite, a local treat in giant whimsical form that rolls into the landscape, is spawned to inquire about adding a new node. When clicked, a new node is automatically added. Users are also prompted when placing nodes by animated feedback, including highlighted topographical signal interference. In the second mode in the reactive scripting prototype app, village residents are invited to consider issues around placement and common accessibility of community infrastructure. Users can undertake dynamic community resource and infrastructure placement with accessibility illustrated, in the absence of fixed footpaths, by the display of animated desire paths. The desire paths, shown here in black, consider land use and topography and reconfigure as the selection of target site is changed. As Majuli is prone to flooding, users are also prompted to consider accessibility and placement under different flooding scenarios. Finding solutions that satisfy all considerations is not easy. Users are thus invited to prioritize relationships in the model and give their own compromise. For example, should an important place have a fixed mesh Wi-Fi node if it will give a weak signal? The user, through winnowing and prioritization, chooses from a solution space that might contain many optimal solutions, those that are optimal for themselves. As a user develops their solutions through iterative participation, they may flag results that best encapsulate their desires and local knowledge. Each is recorded to the cloud with specific design and contextual interaction data to assist decision makers in applying these community preferences. Alongside, a traversable record of user actions is continually captured to allow interaction reconstruction as well as future machine learning and other analysis. The Majuli subject site was inaccessible at the time of research, so a limited study of the proof of concept app was undertaken to test the success of integration and feasibility of the proposed framework. The study was premised on success being indicated by acceptable usability of the app. Although the sample size was relatively small, small groups can be effective in usability testing, with just 10 users potentially encountering at least 82% of problems. The outcome indicates an acceptable level of usability and that the proposed framework can be successfully implemented. This research is based in the context of smart villages and rural development. While the integration and feasibility testing of the proposed reactive scripting framework is in itself valid, a real in-field study would be needed to be undertaken for full verification. By promoting the collection of data that is nuanced by diverse local knowledge and preferences, and through capturing actionable data on local matters directly rather than relying on statistical aggregation or generic models, the proposed reactive scripting framework can afford far more credible responses to unique problems by centralized decision makers.